Now, as we get everybody logged in today and you get started with your opener, we'll start your timer in just a second once we get everybody in. But your opener today is a great example of part of a free response question. Might be a free response question you see on your exam in about a week. Okay. It's a part, there would be a couple other parts to this that we would be finding as well. Okay. But this is a really good place for you to see how you're doing with the work we have been working on the last few days. Okay. With our particle in motion. In this case, it's moving along this line. And you've got the equation that tells us its position, where S is measured in feet and T is measured in seconds. Okay. Now, I'm going to give you 6 minutes to try your opener. As you're working over on the chat side, I'll be sending you a little message to check up on how you were doing, okay, with our opener piece. So let's look at your opener based on responses for answers you all sent. Sounds like we had a little bit of trouble here. Now, as I mentioned when you started, this is an AP free response kind of question. This is exactly what you're going to see on your exam next week. Types of things. So part A, we've got when is the speed increasing? So we need to remember what we know about speed. So remember, speed is the magnitude of velocity, the length of the velocity vector. Well, I don't know what velocity is in this problem, so that's probably a good place to start to find out what's our velocity. Now, we've been looking at the relationship that velocity is the derivative of position. So that means that's not too bad for us to find here. The derivative of t cubed is 3t squared. The derivative of 6t squared is 12t. And the derivative of 9t is 9. And the derivative of negative 6 is 0. So we do have velocity here. So you could do this problem graphically. You could graph the absolute value of v of t. Okay, now, if I added the words, and this would be added if you have a free response question, that you're to justify, then no longer can I do this problem graphically. I can't justify with a graph. Okay. So we'll check it with a graph in just a moment. But as we've talked about speed, we've also talked about speed increases when velocity and acceleration, both vectors, have the same sign. So I need to know about the signs of velocity and acceleration. Well, that's going to require I actually know what acceleration is. Acceleration is the derivative of velocity, the second derivative of position. The derivative of 3t squared is 6t. The derivative of negative 12t is negative 12, and the derivative of 9 is 0. I need to know the signs, the positives and negatives of these two functions. And so what I really want to know first is, when are these equal to 0? When's velocity equal to 0? When is acceleration equal to 0? Because where I'm equal to 0 graphically would be x-intercepts, right, where issues are going to change for positives and negatives, for signs. So 3t squared minus 12t plus 9 is equal to 0. This also is telling us when our particle is at rest. We weren't asked that. I'm going to take and divide everything by 3. So t squared minus 4t plus 3 is equal to 0. And that's just to make my algebra a little easier. because this is a little quadratic. Unfortunately, it factors. So the solving part here isn't going to be overly difficult. And so our particle is at rest at 3 seconds and at 1 second. If we look at when our acceleration is equal to 0, when our derivative of velocity is equal to 0, it's a very simple solve. It's a linear equation. We have t is equal to 2 seconds. Now, honestly, I wasn't really interested in when the particle was at rest or when the velocity was equal to the derivative of velocity, the acceleration was equal to 0. I really want to know the positives and negatives. I want a sign chart. A sign chart for velocity. So I'm going to draw myself just my little x-axis, and a sign chart for acceleration. I do want to label those, and I'm really only interested in a few values on my sign chart. 1 second, 2 seconds, and 3 seconds. So I'm not going to put 0 and -1 and -2 and 4, and I'm just going to deal with the parts I'm interested in. Now, how you fill out this sign chart is completely up to you. You might take and plug in some values into your velocity, like something smaller than 1, like 0. Well, I got +9. That's going to give me a positive. Or you might draw yourself a little sketch of velocity. It's just a quadratic, so it's not like graphing it was really hard. And you can fill out the positives and negatives. Anything between 1 and 2 seconds, I have velocities that are negative. They're below the x-axis. Anything bigger than 3, I have velocities that are positive. Again, for acceleration, you could do the same thing. You could plug in things less than 1, like 0. 6 times 0 minus 12, well, that's negative. Something between 1 and 2, like, I don't know, 1.5. So 9 minus 12, well, that's negative. Or it's just a line. You could draw a graph. Here's our x-intercept at 2. Everything less than 2, our acceleration values are negative. Everything bigger than 2, our acceleration values are positive. I'm interested in where we have the same signs, where velocity and acceleration are working together. And that's happening between 1 and 2 seconds, and from 3 to infinity. So our speed is increasing from 1 to 2 seconds, unioned with 3 to infinity. And my justification is what went on in my head, since velocity and acceleration have the same signs. They're working together, those two vectors. And not only did we find out where speed was increasing, we also justified where that speed is increasing. Now, if you wanted to draw yourself a little graph, you could have sketched out your velocity. That's still going to need to know those x-intercepts at 1 and at 3. Now, that would be our graph of velocity. The absolute value would take all of that portion that's negative and reflect it over the x-axis. So we'd have a graph that looks like this. Well, looky there. We're increasing from 1 to 2 seconds and from 3 to infinity. Now, I can answer the question with a graph. I couldn't justify it with a graph. Right? I still have to deal with signs of velocity and acceleration to justify. And on a free response question, this is probably worth 3 points. You've probably got parts elsewhere where you've actually had to calculate the velocity and acceleration, so they actually would not be checked in this piece. Okay? You're going to have looking that velocity and acceleration are equal to 0, and you would have to actually have equal 0 somewhere in your work. And then the answer, 1 to 2 union with 3 to infinity, and a reason why, because velocity and acceleration have the same sign. Are there any questions at all in part A? Okay, let's talk about part B. And I'm going to give you my suggestion to you in part B. My suggestion in part B is to give yourself a picture. So in part B, I think it's very, very useful here to give yourself a number line. This is what our particle is moving along. And that way you can visualize what's happening here. We want to know the distance that we've traveled over the first 3 seconds from t equals 0 to t is equal to 3. So I need to know, well, where did I start? Where on this number line am I? I need a position. I need s of 0. So 0 cubed minus 6 times 0 squared plus 9 times 0 and minus 6. I started at -6, and this is in feet, but I started right here on my number line. Well, now, I am also going to need to know, well, where did I end? And that is, in this case, we're only looking over the first 3 seconds. So s of 3. So 3 cubed minus 6 times 3 squared plus 9 times 3 minus 6. Or 27 minus 54 plus 27, that's all 0, because that's 54 minus 6. I ended up at the exact same place on my number line. So some of you said the distance is 0. You missed a really important part. What you missed comes up here from our picture. Now, our picture, right, that we did this work for speed also tells me about velocity, the change in position. Okay? Since that's my derivative of position, that's s prime, the change in position divided by the time. Right? In this case, that would be in feet per second. And then acceleration, the derivative of velocity, both those being vectors. This is our change in velocity over time. This would be in feet per second squared. And we looked at those vectors, their signs, positives and negatives, but they also tell us, velocity is positive here when t is equal to 0. So my position is increasing. I'm moving to the right. So when we start out right here, we have a particle that's moving to the right. And it moved to the right in this case for 1 second. I need to know, where was it at 1 second? I need to know our position when time is equal to 1. So we have 1 minus 6, or negative 5, plus 9, which is 4, minus 6, which is negative 2. Our position is that we are negative 2 feet away from 0. Oh, so we moved right out here. We talked about as we did our work, so there's our little vector, okay, and I can count that length. 1, 2, 3, 4. We moved to the right 4 units, 4 feet. Now, if you didn't want to draw a picture, you could have done it algebraically. Where was I on the number line at 1 second? Where was I on the number line at 0 seconds? I don't care about direction. I've moved 4 feet. But from 1 second to 3 seconds, which is actually where we've stopped, we're moving to the left. We're moving now back this direction. We've got another vector. It happens to be the same length, it's just the opposite direction. We're going to figure out how far are we moving to the left, which is also 4 feet. Where were we on the number line when we changed directions? At 1 second. Where did we end up on our number line? Figure out that distance, which is also 4 feet. And we have our total distance, a distance of 8 feet. Now, if we done time more than 3 seconds, we would have changed directions again. So we would have done another piece to the right, however far we'd moved. We've got to know what our particle's doing. Our velocity, the change in distance divided by time. Okay. Acceleration, the change in velocity divided by time. But they are both vectors. That is why with speed, we needed to know their directions. Are they working together or against each other? But when I'm dealing with distance, I only wanted to know the length. That's why we used absolute value. Any questions at all there with your opener? Derivative, the slope of our tangent line for sine of x. Now we're going to talk about the slope of the tangent line anywhere, not at a particular location. And so there are a couple little things I want to review. One, let's talk about a picture. We know what sine of x looks like. So we're going to draw ourselves a little sketch so we know what we're doing. And we'll draw 2 periods here for sine. So sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi of 0. Sine of 3 pi over 2 is -1. Sine of 2 pi is back out to 0. And we can repeat that coming our other direction as well. We have this nice, pretty continuous differentiable curve. Right? No cusps, no corners. Right? And we're wanting to know the slopes of any of these tangent lines. Okay? That's what we're trying to find. Now, keep in mind when we have the sine of x, okay, this is our input. Sine is the name of our function. We don't have multiplication there. And so just a little reminder there for what it is that we're dealing with. Now, we want slope. We've done a lot of slopes. The change in y divided by the change in x. That would be average rate of change. Slopes of secant lines. We want slopes of tangent lines. So we're going to move the points really close together. this would be f prime of x. That's what we want. So f prime, the derivative of sine of x. Anytime we have a function and we just don't know the derivative, we come back to our limits. That is the definition of a derivative. The limit as h approaches 0 of the sine of x plus h minus the sine of x all divided by h. And now, to find the derivative of sine, all we need to do, I need to evaluate a limit. Now, we've evaluated some trig limits before. I can't directly substitute. I get 0 divided by 0. But I know a lot of times when I deal with trig limits, it's helpful to deal with, can I produce one of those special functions, sine of h divided by h. So we're going to try to do that. All right, so we've got the derivative of sine of x. Well, conjugate's not going to help me do that here. I can't factor. I can't use a well-chosen one. I really can't separate this, but wait a minute. I do have a trig identity. I could write what sine of x plus h is. These are two different angles, the sine of alpha plus beta. I know an identity for that. Sine, cosine, cosine, sine. Now, that doesn't allow me to just cancel everything out. In fact, I don't have anything that cancels out. It doesn't allow me to directly substitute, but it does allow me to do a little rewriting. I've now got this first term and this last term that have sine of x's in common, and so I'm going to factor those. So the limit as h approaches 0, the sine of x times cosine of h minus 1 plus cosine x sine h. I haven't produced my goal quite yet. So we'll keep working. But I do have a sine of h over here, so I'm going to use my properties of limits and separate. So we'll make two limits out of this problem. The limit as h approaches 0 of sine of x times cosine of h minus 1 divided by h plus the limit as h approaches 0 of cosine x times sine of h divided by h. Now, over here on the right-hand piece, I can produce my goal. I can separate using my properties of limits. The limit as h approaches 0 of cosine x times the limit as h approaches 0 of sine of h divided by h. There was my goal. So I can deal with that piece. Now over here on the left, I don't have that goal yet, but I'm going to move towards it. I'm going to separate into two limits as well here. So the limit as h approaches 0 of sine of x times the limit as h approaches 0 of cosine of h minus 1 divided by h. Now, I have three limits here in this group. I know exactly how to evaluate. I know what the limit as h approaches 0 of sine of x is. Sine of x doesn't have any h's in it. H is not going to affect that. That's just sine of x. I'm not so sure about this piece, so we're going to come back to that in just a moment. The limit as h approaches 0 of cosine of x is just cosine of x. And the limit as h approaches 0 of sine of h over h is just 1. Now, in this little piece, I don't know what that limit is. And I really wanted signs in the problem, so I'm going to multiply by a conjugate. I'm going to multiply by cosine of h plus 1 over cosine of h plus 1. And so that gives me the limit as h approaches 0 of cosine squared h minus 1 divided by h times the cosine of h plus 1. Now, that still doesn't have me to my goal, but it allows me to get very, very close to my goal now because of trig identities. I know I've got an identity that sine squared plus cosine squared is equal to 1. So cosine squared minus 1 is negative sine squared. And I'm going to go ahead and multiply cosine of x times 1. That's just, of course, cosine. And use my properties of limits, and I can separate now into the goal that I was looking for. I've got the limit as h approaches 0 of sine of h divided by h times the limit as h approaches 0 of negative sine of h divided by cosine of h plus 1, or 1 plus cosine of h. Now, that limit I can directly substitute. So I have sine of x. The limit as h approaches 0, sine of h divided by h is 1. So the opposite of the sine of 0 divided by the cosine of 0 plus 1 plus cosine of x. Well, the sine of 0 is 0. The cosine of 0 is 1. And I've got 0 divided by 2, which is just 0. So I've got sine of x times 0, which is 0. And I now have the derivative of sine of x is equal to cosine of x. It is a trig function. This is a derivative I need to know. And I need to know this not because I don't have other options. I mean, I could, every time I need the derivative of sine, go through evaluating my limit for my difference quotient. But that makes problems that use the derivative of sine in it really, really, really long. Now, pay attention. Excuse me. This is the sine of x. It's not the sine of 2x. It's not the sine of 1/2 x. It's not the sine of x plus pi over 4. We only found the derivative of sine, and it was equal to cosine. Now, are there any questions there calculating the derivative of sine?
Other sine of x.
Well, oh, I wrote plus. It's sine times 0. I accidentally wrote plus there. But we're multiplying. And so we have 0 plus cosine x. All right. I want to give you 2 minutes to try the derivative of cosine of x. All right, so let's look and see how you did. So we can start with our definition of a derivative. The change in y divided by the change in x. We have an identity for the cosine of one angle plus another. Cosine, cosine, sine, sine. And then very similarly, we can factor out a cosine out of those first and last terms. And then separate into limits. We just did the derivative of cosine of h, or 1 minus cosine h over h. So not going back through that work. We have negative cosine of x times 0 minus sine of x, or the derivative of cosine of x is negative sine of x. We need to know that derivative. Now, that's 2 of our trig functions. That's sine and cosine. So let's go to a third one. Let's deal with the derivative of secant of x. Now, we though have been trying to work on a process before we get so abundantly excited about taking derivatives that we should probably see if we can rewrite a function to make the derivative easier. How could you rewrite secant of x? What's it equal to? So tell me an identity. What's secant of x equal to? Secant of x is 1 divided by cosine. Now, we need to stop and ask, does that help us to take the derivative? Do we know how to take the derivative of two things that are divided? Sure we do. That's the quotient rule. So rewriting this function helps us to take the derivative. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. All right, so we've got the derivative of 1. Well, that's just 0. The derivative of cosine we just looked at, that's negative sine divided by cosine squared x. Well, cosine times 0 is 0. Minus 1 times negative sine is just sine. And we have the derivative of secant of x is sine divided by cosine squared. Now, that's correct, but I want to rewrite it. I want to make this look a little simpler. So I'm going to write this as sine divided by cosine times 1 divided by cosine. Because those are simpler trig functions. The derivative of the secant of x, 1 divided by cosine is secant. Sine divided by cosine is tangent. The derivative of secant of x is secant x tangent x. And now we've got half of our trig functions. We know their derivatives. Now tonight, you're going to work on the other half, cosecant, tangent, and cotangent, but I'm going to tell you what the derivatives should be, so you'll know if you get them right. The derivative of sine we already saw, that's cosine. The derivative of cosine we already saw, that's negative sine. Now you're going to work on proving the derivative of tangent, but I'm going to tell you the derivative of tangent is secant squared x. The derivative of cotangent is negative cosecant squared x. We just did the derivative of secant, secant x tangent x. And you're going to find the derivative of cosecant, negative cosecant of x, cotangent of x. Now, I want you to notice something about these 6 trig functions and their co-functions. Right? Sine and cosine are co-functions. Tangent and cotangent are co-functions. Secant and cosecant are co-functions. What do you notice about the derivatives of those co-functions? So again, your chance to speak. What do you notice? The derivative of tangent and cotangent. The derivative of secant and cosecant. The derivative of sine and cosine. What do you see? You guys need to talk. Good. They're opposites. And they're not just opposites. They're opposite co-functions. The co-function with secant is cosecant. The co-function with tangent is cotangent. They're opposite co-functions. So the reality is, while Mr. Epling has told you you do need to memorize these, I only need to know 3 of them. The 3 we did today, well, not quite. I got to figure out tangent. And I will know all of these. Okay. Now, you've got to know these because next semester, when we come back after Christmas, I'm going to tell you negative cosecant squared is the problem. I took the derivative of something and I got negative cosecant squared. You're going to have to be able to tell me you took the derivative of cotangent. Right? So you've got some homework in Math Excel using these trig derivatives. So doing a little practice. Right? And you're going to prove those 3 derivatives. And we'll come back tomorrow and we'll check your little proofs. Okay? All right, guys. Have a great Thursday and I'll see you tomorrow.